Hello guys, and welcome back to Engineering Hack, where we try to solve engineering problems in a way that's hopefully easy to understand. Today we're looking at another nozzle problem in the realm of thermodynamics. The idea of a nozzle is that we will extract some of the internal energy or some of the energy intrinsic to the fluid we're interested in to speed it up. So we're transforming internal energy into kinetic energy. And the problem statement for this one reads, the purpose of a nozzle is to produce a high velocity stream of fluid at the expense of its pressure. Saturated vapor ammonia enters an insulated nozzle at 803.5 kilopascals with a low velocity and the steady rate of 0.01 kilograms per second. The ammonia exits at 290.8 kilopascals and a density of 651 kilograms per meters cubed with a velocity of 450 meters per second. Determine the temperature or quality and the exit area of the nozzle. So let's do a little problem analysis here. First, let's note that we are starting with a saturated vapor. Okay, so we know two important things about the first state or the inlet state. One, the pressure. Second, it's a saturated vapor. With these two, we have the state completely defined. We can grab all the properties we can possibly wish for this first state. Okay. Next up, this is, let me get rid of this. This is an insulated nozzle. What does that mean? Well, if it's insulated, it means that heat cannot travel through the shell of this nozzle, and therefore the heat transfer is nil. So this process that happens inside, in which the energy is being converted into kinetic energy, takes place adiabatically. Okay, what else? The ammonia enters with a low velocity. So the low velocity indicates the kinetic energy is little or negligible. Okay, and we can do an exercise, well, you can do an exercise at home by taking the velocity to be going to zero. So disregard kinetic energy completely. Consider the velocity 1 meter per second. Consider it increasing all the way up to 10 meters per second or so. And then compare what that's going to do against the 450 squared that we're going to get on the exit side. Right, the only one it's even going to make a tiny difference is a 10, and even so it's going to be very tiny when you look at the final result. So bottom line is you can disregard the kinetic energy on the inlet. We have a steady rate, so that means continuity equation can be applied. That means the mass flow rate is going to be 0.01 on the inlet and the outlet. At the exit, we have one thermodynamic property, which is the pressure. So we don't have it completely defined, not yet anyways. And the velocity of 450. We also determine the quality of the exit and the area. Okay, so how do we go about this? We do an energy balance, right? So let me go ahead and say here the velocity on the inlet tends to 0 meters per second. It's not zero or else it would not go through, but it tends to zero, meaning I'm going to disregard the kinetic energy. And if you do a control volume on the nozzle and think about what are the things that are entering and leaving my control volume, I'm going to note that I have the enthalpy of the inlet, call it enthalpy 1, and the kinetic energy of the inlet, kinetic energy 1, and then leaving have the enthalpy on state 2 and kinetic energy on state 2. This one I'm disregarding, so basically what we have is this. right? That's all the energy entering and leaving my control volume. Now, tip for you. When we look at ammonia, it's often tempting to use the ideal gas relationships, but this is a big red flag, right? It's entering as a saturated vapor, and we know it's losing, I shouldn't say losing, giving away or transforming its energy from its internal energy from its molecules into kinetic energy. So we expect it to lower its internal energy, right? And if it's going down on an energy scale, it's going to become a saturated mixture or even a liquid, depending on how far down it goes. So because of that, remember that if we have a liquid, then you don't have a gas anymore, right? So ideal gas does not make sense. So watch out for that. It's something that students often do. Ammonia is always, a red flag to be aware of, and to not jump into ideal gas laws unless you're completely sure that you won't have any sort of liquid involved in the process. Okay, so back to this. If we do the energy balance, the other thing I can consider if I want to is potential energy. We have a whole video showing why potential energy doesn't have to be considered in these kind of situations, nozzles, turbines, etc. You can check it out. And if I were to do my energy balance here, what I would say is that the enthalpy 1 needs to be equal to enthalpy 2 plus kinetic energy 2. Okay, as simple as that. So that means that if I want to know, and note that as we noticed before, we have only one thermodynamic property for the outlet, which is just the pressure. So therefore, if we can find a second one, then we can have this stay completely defined. And if you can have it defined, then I can find out what's the temperature, I can find out what's the quality, and we're happy all about that. And then finally, at the cross-sectional area that I'm looking for, I can just relate the velocity with the volumetric flow rate, or I can relate that to the mass flow rate and a specific volume. Since I know the velocity already, I know the mass flow rate already, I can grab this, which is just another thermodynamic property. Okay, so if I can define H2, I can grab everything I can possibly need to solve this problem. All right, so how do I go about finding enthalpy 2? Well, that's super easy because that's only unknown in this energy balance. It's basically taking the enthalpy on the inlet and removing the kinetic energy of the outlet. That's it. Okay, the only thing I need to be aware of are the units and just grabbing the properties on the property table. That's all. So let's start with grabbing the properties. I'm going to go to the saturated vapor of ammonia table, property table at 803.5 kilopascals. So ammonium, I have it in bar, so 8.035 bar, same thing as 803.5 kilopascals. This is the line I'm interested in. And out of this line, what I'm really looking for is the enthalpy for the saturated vapor. So enthalpy is right here. The saturated vapor one is right here. So this is the column that I'm interested in. And this is the value that I'm interested in right there. So 1461.1, that is given in kilojoules, watch out, kilojoules per kilogram, right? So 1461.1, 1461.1, and that is given in kilojoules per kilograms. Brilliant. Minus, what is the kinetic energy? Mass times the velocity squared divided by 2. If I have this in kilojoules per kilogram, then I don't have the mass component, right? I don't have the mass component. So instead of putting mass V2 squared over 2, I'm just going to put V squared over 2, which will give me obviously something in joules or kilojoules per kilogram. So therefore, I'm just putting 450 squared divided by 2. Okay, but this is going to give me joules, right? Not kilojoules. And we've done this a lot in the past. We need to watch out for the units. this joule here comes from velocity squared, which is meters squared second squared, which we can break into meters per second squared times meters. This is acceleration. This is distance. Acceleration we can break with Newton's second law, etc., etc., etc. We come back to the idea that this is joules and not kilojoules. So for this to be able to, for me to be able to subtract these two terms, I need them both on the same unit. So if I want them both to be on kilojoules, I need to put this to the side here, multiply the whole thing by the fact that 1 kilojoule is 1,000 joules. Okay, so 1 kilojoule is the same thing as 1,000 joules, and that allows me to remove the joules and the joules, and I'll be left with kilojoules per kilogram. So therefore, my enthalpy 2 is about 1360 kilojoules per kilograms. Okay, question that comes up at this point is, Pablo, why didn't you use the mass flow rate? Because you have the mass flow rate, right? And if you were to use the mass flow rate, you can see what's the rate of energy entering and what's the rate of energy leaving. You can, but we're not really interested in the rate of energy at this point, right? If I were to get a rate of energy here, that would not be something useful for me, because what I'm looking for is a thermodynamic property so that I can define the second state or the outlet state. And that would be, if I were to get an answer in watts, that would not be a thermodynamic property. It would be a rate of energy. Okay, so because of that, we want to keep it in kilojoules per kilogram because that's what the tables have. And then we can use this information to now go to the tables and find out what we need to find out for the solving of this problem. Okay, so now what I'm looking for on the table is a combination for ammonia, right? Obviously, because this is still ammonia, nothing changed in that regard. I'm looking for something that is a combination of the enthalpy and the pressure of 290.8 kilopascals or 2.908 bar, which is what the table is given in. So let's go ahead and look for this and then look where this falls on the scale. So 2.908. 2.908. Here we are. 2.908. All right. Now the question is enthalpy. Where does the enthalpy we found fall in this scale here? And the answer is, what did we find? We found it to be 1360. So therefore it falls between these two values. And if it falls between, it's a saturated mixture, right? So we have liquid and we have vapor on the outlet. Okay, so that allows us to answer a couple questions. The first one is, what is the temperature of the outlet? Well, it's going to be -10, because if this is a saturated mixture, then it has to be the saturated mixture temperature. So that's one answer we can give straight off the bat from the property tables, is the temperature 2, or temperature of the outlet, is -10 degrees Celsius.